Thank you very much for the invitation to speak. I slightly changed the title of this talk, but the content is largely the same. Just shortened it a little bit. So the work I'm going to be discussing is mainly been done in collaboration with Tibor Rakowski and Frank Holman, but there are various follow-ups and side projects that have been done with various people in my group. I was until recently based at the University of Birmingham, but I moved my group to King's College London. So if you're in London, stop by, come give a talk or something like that. So, okay. So the revised title of this talk is what classical resources are required to simulate quantum transport. So just a little bit of motivation. So things like conductivities, diffusion constants, these are amongst the most experimentally accessible properties of materials. Very useful to be able to predict these from first principles. Because if we're able to predict these kinds of things from first principles, well, we can more effectively interact with experiments. We can more effectively make predictions for what should happen in a variety of experimental situations. So hopefully it's uncontroversial to say that it's a useful thing to do to come up with numerical algorithms or just ways of predicting these sorts of transport properties from first principles. But of course, the issue is that this is an incredibly difficult problem, because if you want to simulate a quantum many-body system, well, there's a lot of stuff to store. Wave functions contain a great deal of information. And of the well-known existing methods, things like exact evolution, where you store the wave function of a system fully on a computer and evolve it with a big matrix. So things like exact evolution, things like tensor network evolutions, they're all limited in basically the same way, which is that if you want to evolve a wave function to time t, or you want to evolve an operator to time t, then the amount of memory, the amount of stuff you need to store grows exponentially in time. And of course, as the memory requirement grows exponentially in time, so the computational, time taken to do simple operations on these matrices also grows exponentially with time. It becomes very, very difficult very quickly. Right. So let me maybe pose the problem that sort of motivated this talk in a little bit more detail. And so this is how I might try and explain this kind of problem to someone who knows much more about complexity theory than I do. So I'd say the problem we're interested in solving is this. If I look within a class of local, let's say, nearest neighbor Hamiltonians that are translation invariant, let's say they act on qubits, I want to be able to understand how to calculate diffusion constants from first principles to good accuracy. So in such systems, this class of local translation invariant Hamiltonians, I think the generic expectation is that these systems would be ergodic. Another expectation is that they'll have relatively few conserved quantities. So certainly for a Hamiltonian system, energy is conserved, but generically there are only a handful of conserved quantities rather than some infinite tower of conserved quantities. Another generic expectation is that at sufficiently high temperatures, these conservation laws the conserved charges undergo diffusion. This is quite a generic thing to expect, that at high temperature charge and energy diffuse rather than move ballistically. So in this sort of class of problems, I'm interested in this question of what kinds of classical resources, memory, time, is typically required to calculate a diffusion constant to, let's say, accuracy epsilon. That's one part of the problem. And another part of the problem is, how much faster might we be able to accomplish the same task using a quantum simulator? So I'll talk a little bit about both of these today, mainly focusing on this, and then I have a few sort of remarks about the relative performance, possibly of quantum simulators, possibly. All right. Okay. So let me start by just giving you an idea as to how hard it is to calculate a diffusion constant using existing methods. So very little of what I'm going to say on this page is rigorous, but I think this is a story that is consistent with the data that I'm aware of. So let's suppose we want to calculate a diffusion constant for a charge or an element or something like this. Now, there are standard formulae for these kinds of things. So this is a Kubo formula. It's the time integral of some correlation function between the total currents in a system corresponding to the conserved quantity of interest divided by the system volume. So this is the quantity we want. It's in the form of a time interval. One way of approximating this quantity is to truncate that time interval at some finite time t. Okay? So in other words, you take your exact formulation of the problem or your TBD and you calculate this correlation function up to some finite time t and you integrate it and you will get an estimate for the diffusion constant, which should approach the diffusion constant at long times. Now, it turns out that there are various universal statements in hydrodynamics about how this d of t approaches d. Actually, it depends on the dimensionality of the problem and exactly how many conserved charges there are. But for example, in a theory that has charge and energy conservation, the expectation is that d of t minus d approaches 0 as 1 over square root t. Other powers are possible in other situations. 1 over t 3 powers is possible, for example. But these are expectations from hydrodynamics, which are, are at least consistent with numerics, for example, in one-dimensional hydrodynamic systems. Okay, so that's actually some quite useful information because this implies that if we wish to estimate this d, we can just do finite time evolution up to some time that is sufficient such that the right-hand side of this equation is smaller than epsilon. Yeah. I'm at finite temperature in 1D. Yeah, let's just assume for the rest of the talk I'm at infinite. Yeah, cool. All right. So if I want the right-hand side of this inequality to be less than epsilon, and I make epsilon small, then I ought to choose a time that's scaling like this with epsilon. Okay. Right, that ensures that the right-hand side of this is order epsilon. So in other words, you can get an order epsilon accurate estimate of the diffusion constant, provided you simulate your system up to some time that scales as 1 over epsilon squared in this case. All right. So that's good in some ways. We don't have to simulate the system forever in order to get a hydrodynamical coefficient for good precision. But it's actually not such great news because just simulating a system up to some large time is hard on a classical computer because the amount of memory that you need grows exponentially in time. And just to get some intuition as to where this is coming from, if you wanted to calculate this diffusion constant by doing something like, evolving this current operator J at some time t, what would this look like? Well, you take J, which is some sum of local terms, you'd evolve each of those local terms in time, and as you evolve those terms in time, they grow ballistically, or at least within a light cone. And after some time t, this time-evolved operator becomes some complicated superposition of operators that live in this light cone that's of size t. And the number of operators, or the dimension of the space of operators that live in this light cone, is exponential in the size of that light cone. On the leftmost side, I could have identity sigma x, sigma y, sigma z. On the second side, I could have identity sigma x, sigma y, sigma z. There are exponentially many possibilities. So this gives some intuition as to why it is that calculating this quantity on a classical computer becomes very, very costly. Okay. So the expectation then is that the amount of memory you need, or let's say you're doing TBD, amount of bond dimension that you need, will tend to grow in time exponentially, and we can get away with evolving. If we want an epsilon accurate approximation to a diffusion constant, we can get away with evolving our system up to some time t that scales as an inverse power of epsilon. So we might expect that the amount of memory that we need in order to estimate this diffusion constant scales as e to some polynomial in 1 over epsilon. So, just order of magnitude, if you wanted like a 1% accurate approximation or something like that to a diffusion constant, you might have to have at least, I haven't got any constants in here, but you might expect to have an amount of memory that scales as e to the 1, which is obviously very costly. Okay, so we have an algorithm, however, that we think that at least appears to do better than this asymptotically. We believe that you can do much better with classical algorithms.
Can I ask a question? Yeah. How do we know that you can just complete the MPO, maybe this, and this is making some assumption that we allow the MPO to sort of be exact.
Yes, I guess I'm assuming that I need the MPO to have an exponential bond dimension in order to get.
Okay, we know that computing is likely to.
No, I don't think there's any sort of rigorous theory that connects those two points. This is, as I said, not rigorous to get consistent with yeah.
It is polynomial, I understood, and then but there you have the power of 2 half.
Oh, how did I get? Well, so the power that appears here depends on exactly the details of the on some of the details of the hydrodynamical theory. For example, how many conservation laws there are. It could be 1 over t to the 3 halves. So I'm just saying generally it looks like this. The punchline is going to be that well, I'm not going to say. Welch and dramatic tension. Okay. Okay. So we think that we can do better. So just for the sake of the rest of the discussion, I'm going to slightly simplify this situation. I'm not going to talk about evolving a system with a fixed Hamiltonian and look at energy transport. I'm just going to imagine that I have a system which has a single conserved quantity, and let's say that that single conserved quantity is the total SZ component of the system. So like imagine, let's say, an ergodic local U1 flow K spin chain with SZ conservation. Just a little easier to draw the diagrams. And, so this is starting to vibrate for some reason. Okay. All right. So let's take a system with some U1 conservation law, total SZ. And let's suppose that we wish to calculate an accurate approximation to the diffusion constant in this system. So the raw ingredients for any diffusion constant are correlation functions. I wrote down a Kubo formula on the previous page. You can also get the same information by looking at correlation functions between Zs at different positions in the system, different positions and times in the system. So these are the raw ingredients that go into that machinery. Here I'm working at infinite temperature, which is why there isn't an eta minus beta h here, or there is one, but beta can set to 0. And so this is the basic object that we need to calculate and approximate. Now, there's a little bit of a shift in thinking now. So we are going to use the fact that operators can be thought of as living in a Hilbert space of their own, and they undergo unitary dynamics, which we call Heisenberg dynamics in the time evolution. So this correlation function note is a kind of inner product on that space of operators. Right? So it's more than that as well. It's also can be thought of as a transition amplitude. But let me first of all just talk about this, just in case you're not familiar with this idea of a Hilbert space of operators. So when we deal with qubits, usually we have up or down on each side, and so we have 2 to the number of site Hilbert space dimension in our system. If we're dealing with a Hilbert space of operators on the same site on the same space, then on each site we can have an identity, a sigma x, a sigma y, or a sigma z. So it's square root of the Hilbert space dimension, and a complete basis for this space of operators is the space of Pauli strings, which are all the possible operators you can get by picking identity x, y, z on the first site, identity x, y, z on the second site, etc., etc., etc. Okay. All right. So this correlation function that we need to calculate is really a transition amplitude. It's a transition amplitude for the following process. Start with a sigma z operator on site R, evolve it in the Heisenberg picture for time t, and then calculate its overlap with sigma z on site 0. Or in other words, if you take this operator sigma zr and you evolve it to time t, it becomes a big, ugly superposition of operators. Pick out the component on sigma z0. All right, good. So as you know, if you have a quantum mechanics problem and you have a transition amplitude, you can express it as a sum of the parts. You have your time evolution and you cut it into little segments of time evolution. Maybe it's a Trotter decomposition or something like this. You insert a complete set of states, and you get a sum over histories for what happens at each of those intermediate times. The only difference here is that it's a sum over histories in the space of operators. So here is an example of so time is going along the horizontal direction. Sorry, time is going along the horizontal direction in space. It's going along the vertical direction here. So in this picture, sigma z starts at position r, it ums and ahs around a little bit, moves to the left, moves to the right, and ends up at site 0. Okay, a slightly more complicated process would involve sigma z swimming about a bit, splitting into a sigma x and a sigma y. They move around for a little while. They recoalesce and form a sigma z, which then goes to site 0. The third diagram is more complicated. Right. So our claim, and it kind of underlies the approximation that we wish to make is that not all diagrams are giving equal orders of contribution. And in fact, the more complicated diagrams, and I'll be more precise about what I mean by complicated in a second, but the more complicated diagrams are subleading corrections. And so the basic idea is that okay, there we go. Yeah. The basic idea behind our algorithm is that we are going to regularly look at this time evolved operator, and if there is an operator that is that contains more than a certain number of Pauli matrices, we're going to throw it away. Okay, so maybe just make this a bit like this. So for example, yeah, sorry, I got slightly. Okay, good. Yeah, okay. So the basic claim is that the more complicated diagrams give subleading corrections. Okay, and so the basic idea behind our algorithm then is that we are going to throw away those processes which end up involving many Pauli matrices. Okay, so for example, if a process involves more than, let's say, L star Pauli matrices, we will throw it away. And the saving that we make by doing that is that we have to store less information because we are dealing with less complicated operators. The good thing about this is that we believe that the error involved in making this approximation is exponentially suppressed in this L star parameter. So let me just give you an example here. So let's suppose we throw away operators that involve more than 3 Pauli matrices at some time that's denoted by this horizontal line here. So in this first diagram, we're not going to throw away that process because it involves just 1 sigma z Pauli matrix at this time. Second diagram just involves 2 sigma x and sigma y Pauli matrices at this time. The third one involves 1, 2, 3, 4, 5 of them, so we throw away that diagram. Okay, and so we're really constraining ourselves to live in a small subspace of the full Hilbert space of operators, and in doing so, we can save memory. Okay.
So just to be clear, your claim is that, I mean, there are a lot more diagrams of 5.
Yes.
You're saying bring them all the way, actually. Small.
Yes.
Yes.
Small. That's correct. That's correct. Yes. Okay. So. Okay. Oh dear. Oh. Okay. Okay. There we go. Okay. All right. So so the claim, and I'll spend most of the talk discussing this, is that throwing away all of these diagrams which involve more than L star Pauli matrices results in an error in your diffusion constant or your correlation function that scales by e to the minus L star. Okay. Okay. So that's the claim. So let's suppose just for a second that that's actually true. So if that is true, then in order to obtain an epsilon accurate approximation to our diffusion constant, we're going to need L to scale as something like log of 1 over epsilon. Put log of 1 over epsilon in there and you get epsilon. Okay. Right. So we need L star to grow with our desired precision, but it's not growing that quickly. So there's a logarithm in 1 over epsilon. That's not so bad. How much of a memory saving do we make by doing this? Well, we actually make a significant memory saving, as you might expect me to say. So just to recap, if we weren't throwing away these complicated operators, then evolving some operator for time t, we'd get some horrible superposition of exponentially many operators in time in this light cone, and that's a huge exponential in time Hilbert space that we have to deal with. If we just restrict ourselves to the operators in this light cone that involve at most L star Pauli matrices, then the number of states, or the dimension of that Hilbert space, of that operator Hilbert space, actually grows polynomially in time. The intuition for that is as follows. So we're interested in operators that are in this light cone, and let's say there are roughly t sites in the light cone. 2bt light sites in the light cone, where v is some Lie Robinson velocity. So we want operators that have support on less than or equal to L star sites. So take your light cone, order t sites, choose L star of them, and then decide whether to make each of those sites identity X, Y, or Z. So you get this combinatorial 2VT choose L star, 4 to the L, and this goes as roughly T to the L star. So it's polynomial, although it is admittedly a polynomial that grows faster and faster as L star gets bigger. Okay, all right. So now all we need to do is combine these two sorts of estimates together. We need to ensure that L star is greater than log epsilon inverse. And we also have the requirement that the time is larger than that cutoff time that I was calling TC that scales with some polynomial in 1 over epsilon. You know, in order to ensure that our finite time truncation is actually leads to a good approximation. So you combine those two estimates together, and you're going to get something that looks like, okay, so TC goes as 1 over epsilon squared, so it's going to be something like 1 over epsilon squared to some power log 1 over epsilon. And if you put those two things together, you get that the amount of memory that you need to store the state goes as e to the log epsilon inverse all squared. Okay. So just to remind you, for traditional methods like TBD, this would have gone like e to the 1 over epsilon. This is significantly better. Okay, so just to summarize this part of the talk, I provided some naive estimates for what kinds of memory and computation time you require in order to calculate a diffusion constant using existing methods, and it's some sort of e to the polynomial in epsilon inverse. And then for our method, we're proposing that it's e to some log epsilon inverse all squared factor. So this is a good figure. Any questions about that? Yes.
So are you assuming what are you assuming about the physical system? Like this looks like a kind of a translation theory, so you might need some version of it. Maybe you use a Kubo formula, so you already cross the linearity more.
One thing I'm assuming about the system is that it's for the theory that underlies this is that it's ergodic, okay, and that it has diffusive transport.
And that's enough to.
Well, I mean, I'm not saying that our arguments are rigorous. So the arguments that we have best control over are random circuit calculations. Those we can, to some extent, control. And so I suppose there's an assumption that random systems behave like deterministic but complicated ergodic systems. Yeah.
I'm wondering if it's possible if you have a very complicated large weight polystring at some point, which you're throwing away.
Yeah.
Whether it's possible for it to actually, if you would not throw it away, to feed it back to lower weight polystrings. And
that's exactly the computation that we're saying. So really, the probability that an operator gets along and then contracts again is small. Is our statement, and that's what we need. So right. I'll talk about that in a second. Yeah.
Can you just explain again why this is for diffusion or why you believe or what's the main argument why this one goes to
I haven't really explained where this theory comes from yet, but it will be important there. Also, we focus on diffusion because it's some of the generic situation in finite temperature systems that are, like non-integral systems at sufficiently high temperature, certainly in 1D and above a critical temperature in higher.
So you want to also be finite integral.
Yes, okay. That's right. But when I say generic, I'm kind of imposing that because if you randomly selected the translation invariant Hamiltonian, it wouldn't be integrable.
So you're going to explain why those two ingredients are going to be important.
Yes. Yes. Or at least we assume something that's in fact even stronger than just ergodicity. We assume that the dynamics look random and that as operators grow, they end up becoming complicated and effectively random superpositions of other operators. And this is something that we would not be able to assume in an integral system. Okay. Also, actually, sorry, one thing I should correct there. This estimate over here assumes that the system is this asymptotic behavior over here is a standard result from hydrodynamics, and that of course may not apply in integral systems where, for example, the diffusion constant just as often blows up. Yeah. Okay. Okay. Let me say one more speculative thing about actually how the resources needed for these classical computations compared to the sorts of resources you might expect to be able to deploy in a quantum simulator. Now, there, and I have some slides at the end of the talk, which maybe I'll get to. The idea is that you know, if you wanted to, let's suppose you had a quantum simulator and there was no decoherence. So we all like to think about that sometimes to comfort ourselves, but let's suppose that you did have a system that had that capability. So in that case, it turns out that using a similar sort of logic to that I used a few slides ago, that the total number of experimental runs times the total circuit depth that you'd need, so really like the number of layers of gates that you on net have to apply, actually just scales like some polynomial in epsilon inverse, which is of course better than ours. Better than the performance of our algorithm. So I suppose one thing I'm kind of interested in is understanding whether we can have even better classical algorithms, which compare more favorably with this quantum algorithm, or maybe there are even better quantum algorithms which don't use real-time evolution, but which maybe you could get a quantum simulator to perform this tensor network DAOE calculation that we use. DAOE, DAOE, that's the method that we use. Yeah. And maybe there are ways of implementing our numerical technique cleverly on a quantum computer. Okay, now, yeah, I said something vague about decoherence there. In fact, there's a fundamental limitation on the accuracy with which you can get your diffusion constant in a quantum simulator, because, okay, so in order to estimate our diffusion constant to time t, we have to do dynamics to time t, and of course, to this time tc. And of course, if tc is in excess of the decoherence time, we're going to be able to get an absolute accurate approximation to the diffusion constant using real-time evolution. So the decoherence time actually sets a fundamental, well, maybe I shouldn't say fundamental, but sets a bound on the accuracy with which you could hope to get this diffusion constant in your quantum device. Okay. All right. So rest of the talk, I'll discuss more about the nature of the approximations. Sorry, the nature of this argument, which says that by throwing away these complicated processes, you have errors that decay exponentially in our star. Okay. So really, what we're proposing is a physical picture here, which is there's a kind of hierarchy in the space of Feynman diagrams for operators. Namely, they can be organized according to how complicated the history is. So the simpler contributions, those which do not take excursions into the space of long operators, are larger than those processes where you do take excursions into the space of longer operators. And the longer the excursion you take, or the more of these excursions you take, the smaller the diagram. That's the picture that we're putting forward. Okay. So, yeah, so just at a broad level, the idea is that the contributions to this amplitude are suppressed in the size and number of these gray boxes, which denote excursions into the space of long complicated operators. Okay. I should just say a little something about how we actually implement this in practice. So what we do is we encode our operator ZR as an MPO, perform a few steps of time evolution on it using TBD, but for operators as an MPO. Then we apply an MPO which projects this time-evolved operator onto the space of operators which have support on fewer than or equal to L star counting matrices. That's what these horizontal lines are. And we just regularly do this. Time evolution interspersed with projection. And so the idea is that, in this particular trajectory, the projections don't have any effect, but in this trajectory, if this gray box denotes operators that are longer than L star, then we throw this away. This is a trash can. Okay, so we're going to sort of formulate a diagrammatic sort of calculus for diagrams of this form. So this line over here denotes Z, a Z that has been time evolved, and at regular intervals, it has been projected back onto the space of single Z operators. You can almost think of it as a kind of bare propagator for this Z operator in the space of small operators. And the expectation is that at least for sufficiently large time steps, this Baire propagator behaves diffusively. Okay, so this is one of the places where diffusive dynamics comes into play. And so what we're going to want to calculate are the amplitudes for processes like this. Z propagates in the space of single Z operators. Suddenly it undergoes some growth and becomes an operator that's longer than L star. That then shrinks back down to a single Z operator, which then propagates back to Z0. And in fact, you can attach a number to this, much as you would do for a Feynman diagram. That number in this case is involves two Baire propagators, a pair of spatial derivatives, which I'm not going to explain here, and this box, which denotes processes where operators get long and then get short. And to calculate the contribution of this amplitude, you'll have to like sum over these times and over these positions, for example. 1, 1, 5. Okay. So the key thing, it turns out, that you need to understand is what is the sizes of these boxes. In other words, like how this box corresponds to a number. How big is that number? How does it scale with L star? So it turns out that it's exponentially suppressed in L star, and everything else follows from it. Once you have that result, you can show that by throwing away these, we call them backflow processes, the error incurred in your diffusion constant scales exponentially in L star. Okay. So really, this is the fundamental thing we need to calculate. So, of course, if you handed me an ergodic Hamiltonian and said, prove to me that this ergodic Hamiltonian has exponentially suppressed backflow, I would not be able to do that because it's very, very hard to do anything with any particular ergodic many-body Hamiltonian. But the sort of thing that we can try is to estimate the sizes of these backflow processes using random circuits. Okay, so one thing that you can prove is that you start with a Z operator and you look for the amplitude that it gets long and then gets short. If you assume that for the duration of this box, you have local random circuit dynamics, then you can show that on the average anyway, this backflow process is exponentially suppressed in L, and in fact the temporal extent of this box. Okay, so I'm not going to prove that, but I'll give you an intuition as to how the proof for that works, which I'll then try to generalize to a slightly more realistic situation where instead of using random circuit dynamics for this box, I use random circuit dynamics which has U1 conservation, right? Which is an important ingredient in hydrodynamics, of course. So I'll just talk you through this simpler version of the argument first, which hopefully contains a lot of the intuition for why we believe it is that these processes are exponentially suppressed. I have a feeling it's going to surge forward. No, okay, good. All right, and okay, so a consequence for that is that these backflow processes end up leading to corrections to diffusion constants and correlation functions that decay exponentially now. Okay, all right. All right, so let's try to estimate this backflow process. So it's an amplitude for an operator to, over time, delta t over 2, grow to length, we call it, greater than L, and then to shrink back down to the site y over the same time period. So it's the amplitude for that process. So in order to estimate this amplitude, let's insert a complete set of states halfway through this evolution. Okay, but when we insert that complete set of states, remember we are interested in those histories where the operator gets longer than L, because we want to understand, or size out, because we want to understand the contributions from these growth and then shrink processes. So we end up summing over Pauli's at this halfway time that have length of size out. So we want to understand the size of this backflow process. Okay, so what we have here are two transition amplitudes. There's an amplitude for Z to go to this length L Pauli string, and then an amplitude for this length L Pauli string to go down to ZY. Right. So we want to understand the size of this object. Actually, any questions? I realize I slightly fumbled that information. Yes.
I guess this was asked earlier, but so each of these processes is exponentially compressed. So perhaps there's exponentially many of these processes.
This box contains exponentially many processes.
Oh, and you're going to show the whole.
Yeah, I'm not going to a particular operator here. I'm actually summing over all operators that are long here, and there are exponentially many of them.
Okay, and then there's still an exponential.
Yes, yes, that's right, exactly. And you'll see. So this is a fair question, because I'm saying, oh, each of these processes is exponentially suppressed, but there are exponentially many of them. How can it possibly be that? Maybe you could have a conspiracy where actually the exponent, you sum up exponentially small but exponentially many things that can be order 1. But we'll see in a second why that doesn't happen. Yes.
Does the purity of the corresponding constant change?
I'm just doing operator evolution, so I'm making no statements about the initial state except.
Not the initial state. So if the initial state is pure.
Oh, you mean the initial operator?
There's some corresponding initial state, right?
Well, we're starting in an infinite temperature ensemble. So yeah, not pure. Okay. So we want to understand the size of this amplitude, and as I say, I've stripped this down slightly and removed some of the notations. So here's amplitude for Z to go to this Pauli string of length L mu. Here's amplitude for mu to go down to Z. This is the thing that we want to calculate, and the idea is that in ergodic systems we expect the phases on these C's to be uncorrelated. So we expect this to be a big sum of numbers with fluctuating signs, and so it might be small, but we'll make that a bit more precise. So let's, in light of that, let's look at the square of this thing. It seems like a more sensible thing to look at. So if you square this object, you get a sum of a mu primes of operators that contain L Pauli matrices. Get a sum that looks like this. Now the idea, and maybe some of you have seen a computation like this in the study of disordered fermions and pairing of trajectories in and some localization disordered fermion systems. The idea is that when mu is not equal to mu prime, the phases of these amplitudes are uncorrelated and have random signs. And so you're summing up a bunch of numbers with random signs, that's going to give you a small contribution. The idea is that the dominant contribution comes from when mu is equal to mu prime. Okay? So that's an intuition which actually becomes exact when you do a random circuit computation. If you calculate the average behavior of this gamma squared in a random circuit computation, mu is exactly log to mu prime, and you get exactly this expression on the right-hand side. Okay. All right. Okay, so now we have to estimate this thing on the right-hand side, where we just kept the diagonal contribution to this side. And as I say, the path between here and here is exact in the random circuit case without any symmetries. Questions? Yeah.
So this is roughly where you guys saying a random operator doesn't contribute to the diffusion constant, and eventually, as you evolve, you're mainly random operators. Or is there something more?
It might in some way be equivalent to that, although I can't see immediately why it would be equivalent to that. It's more a statement that if you evolve an operator, it becomes a complicated random superposition of Pauli strings, and the signs on those Pauli strings are largely correlated. Okay. All right, so we're now dealing with this rightmost expression here. So if you have this, you have the sum of a mu c squared. We can pull the largest one of these c squareds out if we wish, and obtain an upper bound by doing that. Then we just have a sum of mu over c squared and the largest one of these c's. But it turns out that if you start with some quantum state and you look at the sums of the squares of the amplitudes for that operator to go anywhere, you should get 1. That's conservation probability, right? So in fact, this number over here is bounded above by 1. And so what we really just need to understand is, what the largest one of these operator spreading amplitudes is. And that's something that we can calculate exactly in a random circuit calculation, and which ends up being exponentially suppressed in L and T. Okay, so let me just give you an intuition for why we expect this thing to be exponentially suppressed at least in L. And well, the idea is that as the operator grows, there are exponentially many. In order for Z to go to an operator that has L Pauli strings in it, it needs to grow for a time that's consistent with Lee Robinson bound. It has to grow for, you have to evolve it for long enough such that it can get to size L. Right? Okay. So that's where this inequality comes from. And the idea is that it has become a random superpositions of Pauli's in this lifetime. And so there are exponentially many in L Pauli's in this lifetime. So provided each of them have roughly the same amplitude or similar amplitudes, then we expect C to be exponentially suppressed, because we know that the sums of the C's have to be less than or equal to 1. That was conservation probability. So if each of these is typically the same size, then each one has to be exponentially smaller now. Okay. All right. Questions about that? So anyway, regarding your question, a thing that was key here was the collapse of that sum to just the diagonal terms. And that ends up giving you basically an extra factor of the C squared, which, yeah, allows sorry, oh no. Yeah.
I guess your key assumption is the diagonal approximation, right? So,
Yes.
We have another body dynamics, then the correction to that, I mean, why does it break down is because we have this other one.
Yeah, I'll get to that in a second. Yes, yes.
Would you not now have some problem with relevance? I mean, you're not talking about the typical overlap, right? You have a huge number of returns.
Yes. Yes. But that's actually the main reason why this is just an intuitive argument rather than in the random circuit calculation, where you end up looking at the sup of the average value of the squared. Yeah, and that's something you can calculate exactly in random circuit calculations. Okay. Now, right. Okay, so putting all of those estimates back in, we find that this box is actually exponentially suppressed in L. Then some overall L that are larger than or equal to L star, and you'll still get something that is exponentially suppressed in L star. Yeah.
So I'm thinking about an example that maybe special operators that you cannot cancel the place. So for example, if you have a D operator. Yeah,
I'm about to talk about this. If the argument you're about to make is specific to the U1 case, yeah. Yes, I'm about to talk about it. Yeah, good. All right, good. All right, so indeed, there was a strong assumption here of random phases. We assumed that this sum collapsed to just the diagonal terms. And certainly for like a particular ergodic Hamiltonian, this is a very strong assumption, but it's even a wrong assumption if you take a circuit that's as random as possible, but which has U1 conservation, right? So even in a random circuit computation where you impose U1 symmetry, this diagonal assumption is not true. Okay. So here we have less control over the calculation, and I'd really like to work with someone who's also sort of experienced with random circuit computations and actually try and work this out and prove it, because I think it would really strengthen the case for our argument. So I'll just give you I will give you an idea of what we think happens in this case. So it turns out you don't get a full collapse onto diagonal terms, but you do sort of get a partial collapse. So not all of these terms survive, just a few of them survive after U1 circuit averaging. Here it's sort of useful to use a slightly different basis for operators on site. So we'll have, instead of identity XYZ, we'll have identity sigma plus sigma minus sigma Z. Okay, so U will now be strings of these operators. And so what happens in the random circuit computation for this is we don't quite get a collapse onto the diagonal terms, but we do get a partial collapse where basically, so we have the sum of a mu and mu prime, and it turns out that the terms that survive have mu and mu prime matching in where they have sigma plus sigma minus matrices. Okay, and so this is an example, for example, I think you were thinking, if I had an all Z operator, there wouldn't actually be any cancellation between C and C star. And this is an example because identity and Z don't differ by any sigma pluses or sigma minuses. They just differ by multiplication by this conserved quantity Z. Yeah.
That's the meaning of the model of transport, right? I mean, you want to study transport, you should have at least one.
Yes. Okay, so this sort of path. So just maybe an idea. If I had sigma plus on site 1, Z on site 3, sigma minus on site 9 for my mu, and I had sigma 1 plus Z1, Z7, sigma 9 minus for my mu prime, this term would actually survive because they have the same location for the sigma pluses and sigma minuses. Okay, good. So I'm not going to be able to go through all of this. This is actually sort of detailed in the paper. I don't like going through it because it's not at all controlled. It's based, you know, I make some quite strong assumptions about the uniformity of these coefficients, the sort of level to which they're all the same, the distribution of these coefficients, the sizes of these coefficients. But you can make an argument that makes it look like it's exponentially suppressed in L. I'm not sure. I'm not sure how valid that argument is. It seems like the most plausible fit to the data that we have and to the limited theory that we have. But that's.
I have a follow-up question. So I'm not sure whether it will suppress exponentially with the distance, but I think that we will have only a follow-up for the time duration of that bubble.
But if it's a strong enough power law decay, it you know, if it was a power law decay that's like, let's say at least t to the minus 3 power or something like this, then it's sufficient.
Why is it?
Because are you saying why can I assume that this box is small in time?
Yes.
Yeah. So if it's sufficiently fastly power law decaying, then you can truncate the box.
I guess we'll change the arrow scaling with respect to
No, not so much. No. So maybe just to, you know, if I have an autocorrelation function between like a string of, let's say, LZs and another string of LZs, then the decay of that in time, you know, it goes to like t to the minus L star over 2 or L over 2. That's a very fast. These long hydrodynamic strings still have a very fast decay rate
I'm thinking about splitting, for example, the C operator into independent sum of C operators. It's like you're splitting a random walk into, let's say, K random walk.
Yes. I understand what you're saying. Yeah. So what I'm saying is that those long Z operators, so your Z is split into a bunch of Zs, and you want to understand what is the contribution to this process where you have these long Zs and they propagate in time for some period of time. And I guess you're saying that that will be power law decaying in time. What I'm saying is that it's a very large power law. It's something like t to the L star.
But here you assume that L would be proportional to t in your Lagrangian time.
Oh, yeah. No. That I think is a fair. That's a fair comment. Yeah. That's something that has made me uncomfortable. Like one thing that we assume in that argument is that in fact, yeah, for this diagram you may as well assume that t is scaling like L. Yeah, that's a fair comment. I don't have a big response to that. Okay, so better hurry up a little bit. So anyway, this diagrammatic calculus actually gives you some firm predictions for how the corrections decay in L, but also how they decay in time. And it turns out that it, you know, depends on various things like how many conserved quantities you have, but also whether or not your dynamics are deterministic, i.e. you have some fixed Hamiltonian or fixed unitary, or whether or not you have some noise in the problem, like if it's a random circuit problem. So we have distinct predictions for those cases, and the random unitary circuit ones we can actually check and they turn out to be correct. We also have predictions for how your time-dependent diffusion constant, how well it converges with L to the true value of your time-dependent diffusion constant. So now what I'll do is just present some numerical data. Yeah. Okay. Yeah. So yeah, the evidence we haven't. I don't know why this is buzzing. Okay. So our picture is so far as we have been able to check, supported by numerics. We also have this independent, but also unfortunately uncontrolled diagrammatic argument in our paper. Basically, what we do there is we look at the operator spreading problem for the U1 random circuit, map it to something that looks like a stochastic model, not quite stochastic, it actually has some signs in it, and then look at a subset of the diagrams that contribute to these backflow processes. So here's an example of such a diagram. There are different colors on here because it's a replicated calculation, so there are two replicas, so different colors represent two different replicas. Anyway, you can calculate contributions from subsets of diagrams, some of which look like this, and argue that they are exponentially suppressed in L. And that argument we're in pretty good control of, and it has strong numerical backing. But I'm not going to be able to talk about that today. But see the paper for more of that. Okay, so I'll briefly go through the numerical evidence. The things that I'll plot come in two types. One is just, what's the difference between does anyone understand why it's beeping at me? Okay, pretty. Okay. So big finish. Okay. So there's the one thing that we can look at is the error in our diffusion constant using Dowie versus not using Dowie. So I'll call that delta D. And another thing that we can look at, which is sometimes numerically easier to look at, is what is the error in the diffusion constant due to acting with a dissipator once halfway through the time evolution. So we have predictions for these various things. There's also error in correlation functions due to single dissipation event, which is kind of similar to this. That will be denoted C greater than L. We have predictions for these. All of these have the feature that they're exponentially decaying in L, and they have various power laws depending on whether you're looking at a random circuit system or a deterministic system. As I say, the power laws in the stochastic case all check out. The power laws in the deterministic system, less so, but that's largely because we can't push the numerics for long enough times to resolve the power laws. Right, that's the original problem. We can't do time evolution exactly. And
when you say dissipation, I guess you mean energy dissipation. Is the thought that if you have the phasing, that won't really change?
Oh no, sorry. I mean, when I say regular, I mean regular in time. So just every few time steps, doing some applying this Dowie operator. Yeah, sorry. Yeah. Okay. So here are some deterministic stuff on specific spin chains. Yes. Yeah.
But how do you get the predictions for the BAU now?
Oh, those come from the Feynman diagram that I drew down. I wrote down box multiplied by 2 propagators. So it comes from bounding that. Okay, all right. And actually, the source of the difference between these powers is quite interesting. I'm happy to talk about it at the end. Yeah. Okay, let me just quickly go through the data. So this is the error in a correlation function due to throwing away long operators halfway through the time evolution. Okay. For a deterministic spin chain, this is a spin chain that most people say is an ergodic spin chain. Okay. 9 out of 10 people that meet in the street will say this is an ergodic spin chain. This is the correlation function as a function of time. You can see it's quite noisy. This is the maximum value of that correlation function as a function of time. And we expect this curve to decay exponentially in L star. And well, it looks consistent with exponential decay in L star. But of course, if you only have a decade of data, stating a difference between a power law and an exponential could be dangerous. But so far as we can tell, this is exponential in L star. Here it is for a slightly different model, which also exponentially decays, although interestingly at a rather slow rate. And for some reason, the correlation function data look a lot nicer in this case. We don't really understand that. Okay, so this is our evidence of deterministic spin chains. We also have evidence from U1 random unitary circuits. This is that error in a dissipation constant, in a diffusion constant due to one truncation event. We end up for this quantity predicting a decay of t to the minus 5, t to the minus 5 halves. And you can see that it's actually a pretty good power law decay. We can go to quite long times for these random unitary circuit calculations because it turns out many of you may have heard that for random unitary calculations, many of the computations that you make map onto something that looks like a StatMech model. You can push system numerics in times to long times and get convergence, which is what allows us to pull out these power laws. So the power laws agree as they should do for different L star. And also, so far as we can tell, it's rapid exponential decay, although again, here we're dealing with even less L star. It turns out that because in the random unitary circuit problem, you have to double the system, this MPO that applies the dissipator is rather more costly. So we're more limited in the L star that we can use in this case, unfortunately. Although if someone who is more competent than I am at numerics tried this, I'm sure that they could get larger L star and either confirm or disprove our conjecture. Okay. One thing I should just advertise is that Frank, me, Tibor, Isabella, the rest of our groups are doing, I think, a very noble task. We're trying to benchmark various numerical techniques against one another. Because of course, if I tell you the diffusion constant for the tilted Ising model is, 0.99, something like this, how are you going to verify that that's correct unless you have an excellent quantum simulator or a real system that really does precisely simulate that Hamiltonian? So the best that we can do is just try and compare various methods against one another that are on the market. And so these are various methods: truncated Wigner, ED, non-equilibrium steady state. That's something that Homage and Marco implemented. There's also something which we don't have a name for, but Jens Bartesen and also on the paper, so we call it Jens. And so, yeah, a striking thing about a lot of these data is that there is actually a surprising degree of agreement between the different methods, although we do find some interesting discrepancies in some situations, particularly in integrable systems. All of the numerical methods seem to do just about equally badly. Although I would say that in the integrable case, we actually have exact predictions, and I would say that Dowey actually does seem to do better in this case than the other methods, even though we don't have any reason to believe it will work for integrable systems. Anyway, so I should probably hurry up a bit. A really cool thing to be able to do would be to actually benchmark some of this data against predictions from quantum simulators. So I don't know if that's possible in the short term, but it would be cool to have another point on these figures that was from a completely different method. Because if we get agreement in that case, then we can be sure that the quantum computers are doing pretty well and that our numerical methods are doing pretty well. Yeah, okay. Okay, so that's pretty much the end of my talk. The upshot is that we think we have an algorithm which more efficiently allows you to calculate accurate estimates of diffusion constants. And we have some arguments of varying degrees of rigor, and yeah, I mean, it would be really great to have to make some of these U1 random unitary circuit arguments rigorous. That's something that we're still working on, but yeah, if anyone is actually interested in that, please come and talk to me. That's a meeting person power. Okay, so that's the end of the talk. Yeah.
Is it also true that as you increase L star, does your convergence of the diffusion constant that you estimate from numerics, does that converge exponentially fast?
So yeah, I put some of the details of numerical implementation under the carpet. So what we actually do is we have a parameter that determines how strongly we dissipate long operators. So we actually implement this softly. So maybe draw a picture. You're there. Maybe that's that. Okay. Not a good start. Okay. So this parameter we call gamma. Gamma large means that we just throw away operators that are longer than L star exactly. Gamma small means we sort of do this with a probability that roughly eats the minus gamma. Okay. So we have we're plotting diffusion constant as a function of gamma. Our estimate of diffusion constant as a function of gamma. And we do this for different L stars. Okay. So we get we can't do really small gamma because that's the same as doing TBD. So there's a sort of exclusion zone here. And so we get a sort of functions of, this is the L star is equal to 1 curve. Then we get an L star is equal to 2 curve, this kind of thing. And what we find is that the curves get flatter and flatter as, or at least narrower and narrower as L star gets bigger. One conjecture might be that gradient is actually exponentially decaying in L star. But as we only ever typically go up to, L star is equal to 5, but sufficiently large L star, the MPO itself becomes problematic, or actually adds, it becomes a more complicated MPO. The bond dimension increases with L star. But so far as we're able to tell and get converged data in bond dimension, the curves get flatter and flatter and flatter. Actually, this provides a sort of cross check on our answer, because we end up estimating diffusion constant with different L star, and then one indicator as to whether the method is working or not working is if those different predictions don't line up. One thing we find, for example, in integrable systems is that the different L star data are all completely different. And that gives us an indication that this method and the theory behind it is not working very well. And these other ergodic examples that I showed you on a few slides ago, they end up being very good agreement between them. Like, you know, when I say good agreement, I mean like a few %. Yeah. Yes. So it's a sort of, it's kind of, well, it's our best attempt at a cross check. Yeah.
So, Ray, I might have guessed that if you just did TDD with completing the bond dimension, that you're going to get something morally similar. Yes. Is that one of these points on the numerical data?
No, I don't think you do get something morally similar to this. So for example, well, when you plot diffusion constant as a function of time. So idea is that probably the exact curve of something like this. Okay. What we tend to find for TBD is goes kind of crazy, doesn't end up plateauing. So it's actually hard to even say what the estimate for the diffusion constant is. What we found for Dowie, one nice thing about Dowie is that actually you might end up converging to the wrong diffusion constant, but you actually do end up diffusing eventually. So you can actually like it.
All the lowly things. You might have thought that TBD should keep all the lowly things and other stuff, but that's really not what's happening.
Yeah.
I don't know what's going on.
We don't have a theory for that. We really don't. I mean, I think that's, yeah, I'd say that that's like a cool open problem, like figuring out the relationship between, you know, if I tell you that my TBD truncation error is blah, how is that reflected in like hydrodynamics?
Somehow it's not keeping all the lowly things.
Yeah. It's actually throwing away important hydro information. Whereas what we're doing is selectively trying to keep the important hydro information. And so that's why we think our.
It'd be interesting to understand.
Yeah. Exactly. Yeah.
Does TDVP plateau?
TDVP is even crazier.
Oh.
Actually, yeah. Of course, actually, it depends on which model you study. There was that example of the tilted field Ising model, which had rather pathological behavior, which, you know, looks like a diffusion very quickly, but actually just generic models end up leading to quite a wildly fluctuating curve. Yeah, we don't. But that's one of the reasons we don't do TDVP as one of our benchmarks, because it is actually quite wildly optimal. Yeah. Oh, sorry.
Well, yeah, I'm going to ask a question by the long shot. Can you go beyond speech and just do models like this model we have discussed? Right? Of course, I understand there is a problem because it's not the system, but still the data which we seem to have got from TDP so
yeah,
there has to be some reason why it was so easy to simulate.
Yeah. Yeah, possibly, but it really does have to be a different version of our method. I can tell you one horror story from simulating XXC with our method. So, XXC in the diffusive regime. Yeah. So, yeah. So here's a curious thing. So if you do Dowie in XXC at delta is 2, the L star is equal to Q curve looks something like this, like pretty innocuous. You end up getting diffusion. It asymptotes to the wrong diffusion constant, but it's not that far off, actually. If you do L star is equal to 3, you get something. Oh, I should do a different color. That'd be more sensible. If you do L star is equal to 3, you get some wild behavior like this. Actually, subdiffusion. Okay, this is L star is equal to 3. You do L star is equal to 4, you get diffusion again for some reason. I'm not sure if it's lower or higher, but it looks sensible again. So there's something, yeah. So this has led us to think that there's something maybe there's a conserved operator on 4 sites that's very, very important for the dynamics here. But in any case, we can't use our method as it currently stands. In fact, it works pretty well at the isotropic point, but not in the diffusive regime. Like we get KPZ as well, or T to the 2/3. Okay. We do get that, but we don't. The diffusive regime doesn't work well for us.
Diffusive regime is weird.
Yeah. We haven't tried yet. Actually, the first thing we're trying to do is finite temperature in 1D. But I guess there's no like fundamental obstacle to putting it on a cylinder. We haven't tried, but there might be some reason to expect it to actually work better. Various results and operator spreading that I think that Adam have formulated. But yeah, I'm not sure. But we can try.
There's a question in the chat.
Oh yeah, sure.
Mike Collins. Can you comment on typicality proofs / arguments in random circuits? It seems like you've been studying mean behavior or correlation.
Yeah, mean squared behavior. Or what we looked at is the average size of the return amplitude squared. I can't really comment on average versus typical math. For the random circuit case, without symmetries, I'd be very surprised if the variance kills you. In fact, I think we might have looked at a version of this problem like a long time ago and found that the fluctuations are small. In the U1 symmetric case, I have no idea. Even the 2 replica case is hard enough to formulate and solve numerically. I don't know, but if someone wants to do that, they should. That would be interesting to know. Yeah, I guess my main hope is that 2 replica U1 symmetric case is actually maybe some solvable model. Maybe there is some happening to a solvable model. It's like relatively simple. Yes, I